I'm Peter Tefft, and I'm here to talk to you about in-app protection. So, yeah, let's get started. I'll tell you a little bit about me. I'm a software engineer at Preemptive. We build app protection software. The product on which I primarily work is called Preemptive Protection-O for Android and Java, or PPDAJ. It used to just be called -O. I'll still call it -O colloquially. So I play a lot of board games. If that's something that you want to talk to me about afterwards, we could do that. Just stop by the booth. So there are a few things I hope you'll take away today. I want to give you a basic notion of some ways in which attackers might approach your app, the risks that those attacks pose to your app, what they mean in terms of concrete damage to you, your customers, and a set of tools and techniques that you can use to protect your app. So this might be, in some ways, a bit more basic than some other security talks at this conference, but I don't think that's a bad thing. So let's start out. What do attackers try to do? So if you have any kind of intellectual property in your app, any proprietary algorithms or workflows, they might try to steal those, copy them for their own purposes. We have some customers who have very proprietary methods for determining the viability of an oil field, for instance. And they definitely want to keep those out of the hands of their competitors. Attackers might try to produce copycat or counterfeit applications, and I'm dividing those up, I guess, by purpose, right? A copycat application kind of works on the back of your IP, but provides potential value to a customer. It's really you who's getting hurt. Counterfeit application is what I'm qualifying as something that acts like your application, but maybe does something malicious. Maybe it's there to harvest user credentials. Maybe it serves ads that benefit the distributor rather than you. Maybe it's malware. So attackers might try to discover security vulnerabilities in your app. So that could be security vulnerabilities on the client side. Maybe you're storing something improperly. Maybe it's something on the server side. Maybe an attacker is reverse engineering your app to see how it is interacting with your server-side components. If they can scrape an API from your app, figure out what your endpoints are, then they have a jumping off point to attack all of your APIs. So a lot of that is in service of stealing sensitive data, which, discovering security vulnerabilities is, a big part of that. If you're storing something improperly or communicating insecurely with something, then that allows an attacker a way to intercept your data. So I'm going to cover some ways in which, first I'm going to cover static analysis as a way that an attacker will try to understand your app. So there are a lot of automated tools that will scan your application to determine security vulnerabilities. LinkedIn's Quark comes to mind. These are valuable tools for finding vulnerabilities in your own app. Certainly, they can also be used by an attacker to find similar vulnerabilities. Today, I'm going to go with something pretty basic. Let's talk about decompilation. So decompilation is the process of reproducing source code from compiled code. In the context of Android apps, we're generally talking about converting DEX code packaged within the APK to Java bytecode, and then converting that into Java source code. There are a lot of tools that just handle that conversion out of the box, which I'll show you shortly. I've listed a few different decompilers. I don't feel a particular need to go in any deep detail on any of them. Decompilation makes your code easy to understand, so if there's anything that you'd prefer an attacker didn't understand, hindering decompilation is important. It makes it, therefore, easy to find vulnerabilities within. It makes your code easy to copy, modify, and rebuild. If I have source code for your classes, then I can pretty easily rebuild them with modifications and use that to create possibly counterfeit or modified versions of your code. So we're going to do a quick demo. I've been told that I'm brave for doing any kind of live demo here, but this one is pretty basic. So I put together, there we go. Okay, so I put together a simple mock banking app. I call it Money Bank, which is a dumb name, I'll admit, but Dollar Bank is a real thing, so I think I'm okay. So it's pretty simple. I have a service on my machine that this talks to. I'm going to log in with some basic credentials, and it's going to hit an API on my machine and retrieve a list of accounts with balances and account numbers. Pretty simple stuff. We're going to see what it looks like in a decompiler. So I have Bytecode Viewer open here. Bytecode Viewer is a really nice UI for doing decompilation in general and navigating a set of decompiled code. I'm going to click and drag our unprotected APK over here, and it'll take a sec. Bytecode Viewer will do the work of converting the DEX within the APK to Java bytecode using dexajar, and from there allow us to view classes through a decompiler. I think it should almost be done. There it goes. So we have a whole package tree. It's not just our classes, it's classes of any kind of library that we consume. So if I expand this, I see a variety of classes relating to login functionality. If I open up this login data source class, we can see, let's see, can I zoom this? I cannot. So we can see that this class is responsible for essentially assembling our HTTP request to log in and ultimately grab an access token. You can see that we're putting a username and a password into a JSON object, and we're passing it to this URL. Looks kind of funny because it's on my machine. So yeah, it's really, really easy to reproduce source code from an APK. So let's talk about some static defenses. So renaming obfuscation is one that you're most likely to be familiar with. It comes pretty much out of the box in an Android context. It's offered by ProGuard and its replacement R8. If you're not familiar with R8, it's, as I said, a stand-in replacement for ProGuard. You might have switched to it without realizing it if you were previously using ProGuard. So renaming obfuscation renames classes, methods, and fields. It tends to rename things from long semantic names like com, preemptive, crypto, super secret, cipher to short meaningless names like A. I would say that it works well alongside other obfuscation techniques, and I wouldn't try to apply obfuscation to a code base without it, but it's a pretty incomplete solution. In fact, when creating R8, Google has been pretty open that the purpose for them is not actually obfuscating your code so much as it's shrinking it, right? It's the name of the setting to enable R8 in your Gradle build script is minify enabled, not obfuscate. But still, it's valuable. We're going to be looking at the same APK with renaming obfuscation applied. I've used some non-default rules here. specifically repackage classes, which will allow R8 to move as many classes as possible into the default package, and that will make the structure of the app a bit harder to understand. I've also added allow access modification, which will essentially enhance that effect. If you're able to move classes out of a package by making members or classes public, then R8 is able to do more in terms of this repackaging. So, I have this one prepared already. So if I expand this, we still have some things in the original packages naturally. That's a function of them being entry points into the app mentioned in the resources or the manifest. But the vast majority of classes are in the default package, and they have, again, meaningless names. This is pretty hard to navigate at a glance. But to show you why that might not be sufficient, Bytecode Viewer has a nice string search function. So I'm going to go ahead and type username into this, and it's going to find our login data source class again. And we can still see a lot of what it's doing. You know, it's maybe not so, there's really a lot of clarity here. I can still see that we're putting a username and a password into a hash map, that we're constructing a JSON object. JSON object and hash map are part of the SDK, so we can't rename them. So let's see if we can do a little bit better. So, string encryption. String encryption replaces string constants with encrypted versions, essentially to remove the kind of insight that we got from those string constants in the decompiled source code. So it requires some additional instructions to be added to the code to decrypt the strings, but not too many. So we're also going to apply some control flow obfuscation. So control flow obfuscation changes the flow of method code. It can frustrate some decompilers or stop them. It really depends on, to some degree, on the initial complexity of the methods involved. And there's kind of a greater performance penalty when you're dealing with control flow obfuscation than you tend to get with string encryption, because you add a lot of, frankly, redundant instructions. A lot of decisions in the code to determine the next instruction, and a lot of instructions that won't get hit. So we're going to apply these obfuscation techniques to our app. I'm going to go ahead and launch -O. And it comes up with a wizard. So I select an Android project, navigate to our app's Gradle build script, and choose that. Let me just make sure. Oh. Okay. And then this summarizes what it's going to do. It's essentially going to patch our Gradle build script and generate a configuration file. And yeah, it prompts us to run a build so that if we wanted to add more configuration settings to this file, then we have a list of classes on which to build that. Essentially populates the UI. But really, this applies a baseline level of protection that already, we're essentially done with the most basic protection. Go ahead and assemble this APK. Oh, Shouldn't take too long, but it is a live demo. Dash-O is running, and it should pass things off to R8 shortly. Yep. Okay. So go ahead and open this in bytecode viewer. And while that's essentially dedexing, I'll go ahead and open a mapping file. So I'm not going to be able to, I don't know that I can actually find our original class by navigating through bytecode viewer. I'm going to cheat a little bit. This is a mapping file generated by R8. It shows the original class names and the class names after renaming. So this was, the login data source class was renamed to KN. Yeah, as you can see, we got a big pile of classes in the default package. And yeah, this is pretty mangled. We can see that we're putting some things into a hash map still, and yeah, you can see that there's something with a JSON object down there, but overall, pretty difficult to read. So that's going to help protect against some static analysis on your code. Let's talk about some, I guess, runtime analysis. So, if people are trying to determine what your app is doing at runtime, they can do a few things. Debugging tools are a good starting point. These are the same tools that you use during development. They allow you to attach breakpoints, examine local variable states, really see a whole lot of things that are going on in memory. Hooking tools offer, well, help you achieve some similar goals. I think Frida is probably the most popular one at this point. They allow you to attach callbacks to methods in an app so that you can cause them to respond differently, essentially. Maybe you want to cancel out the default behavior of something. Maybe you want to have Frida spit out information about what was passed to a given method. There's a lot that you can do with them. I think someone posted an article to Medium over the weekend about, hey, here's a script that you can run to, they claimed it was a universal way to disable SSL pinning in an Android app, which seems like a tough sell to me, but let's see. So in general, they allow you to inspect and modify data at runtime. This could be potentially sensitive data. And again, modifying app behavior allows you to circumvent checks like SSL pinning. So attackers might also try to tamper with your app, and I mean something pretty broad with tampering. Your app can be repackaged after some alterations, and I hope to do a demo of that shortly. So yeah, it's not hard to change code, the manifest of your app, tamper with the resources. They'll naturally need to be signed with a different certificate, but if you're publishing a copyright app that's, or not a copyright, counterfeit app is the word I'm looking for, then that's pretty par for the course. You're going to want a different package ID anyway. So your app can also be manipulated externally, especially in a rooted environment. In a rooted environment, all of the protections that come with running on Android kind of disappear, all the partitioning. Another app with escalated privileges could pretty easily peer into what your app is doing at runtime. And so these are things that the user may or may not be complicit in. Maybe you're in a situation where, where someone wants to essentially crack your app and bypass license checks. Maybe they want to tamper with your app to harvest data flowing through it. If I run a video streaming service and someone wants to circumvent the DRM protection that I put on the video that my app is consuming, then they might want to create a cracked version of it or launch the app from a rooted context using an app built for that purpose. So I'm going to do a quick demo where we're going to essentially make a counterfeit version of this money bank app that's going to do something malicious. And I think I'm going to need my black hat for this part of the presentation. So, I have source code here for a modified version of this class, which is called request queue singleton. The purpose of this class is to wrap a volley request queue so that we're not creating request queues throughout the app. If you're unfamiliar, Volley is an Android networking library. In this case, we're using it to handle our HTTP requests to log in and retrieve balance information. So I've highlighted the portions of the code that I've added. Again, I've taken the code for this, the original code for this class from a decompiler and essentially inserted some new lines. So this is the add to request queue method, essentially adding a request to our one request queue. I've added something that will essentially determine if the request is a JSON object request, and if it is, try to extract a body from it and post it to another server running on my machine. So this is, this is essentially just going to spit out the content of whatever request it receives to the terminal window. Just for demonstration purposes, it's kind of a command and control server, if you will. So I have a Gradle build here that is going to, I'll walk you through it. Essentially, it builds our class against the classes in Volley. I extracted the classes.jar from the AAR since the Java plugin doesn't like a bunch of resources and other stuff stuffed into its dependencies. I've also building against the Android SDK. So this script unpacks the dex from an original APK, uses dex.jar to convert it to a jar, unpacks the classes from the jar, and makes a new jar with our modified class. Then uses dex.jar to turn that back into dex, ultimately repackaging the APK. I just realized I think I used the wrong task. And yeah, at the end of it, it is ultimately re-signing it with a different certificate than the original. Oh. You guys ready to go home? All right. So I'm going to go ahead and install this on the emulator here, and we'll go ahead and watch this node endpoint. So I'm going to go ahead and log in. And yeah, it's posted our credentials to this server. They're compromised. So, yeah, runtime attacks matter for a lot of reasons. They can undermine your static protections in general. So one thing that I didn't really cover, if I've gone to the trouble of putting string encryption on my app and someone attaches a debugger to it and can inspect all these values in memory, then they can pretty easily get plain text values of those string constants just by stepping through. Any sensitive data that you have in memory can be pretty easily accessed. And ultimately, yeah, they allow you to circumvent the intended behavior of the app. They can enable cheating in games, which, if you have a successful game, especially a multiplayer one, and people find that a lot of people are, cheating on it, then they're not going to want to play it anymore. That's why I quit Rust personally. So let's talk about some runtime defenses. So really what I'm going to be talking to you about today is runtime checks. So you want to try to check your environment at runtime. If the device that you're on is rooted or an emulator, you might want to stop there. Rooted devices, again, are particularly insecure environments. Extremely untrustworthy. Emulators, maybe a bit less so, but for the most part, you don't expect your regular users to use emulators. They're really, I think some people use them for gaming. For the most part, someone is doing something to reverse engineer your app and they're using an emulator. You might want to check the integrity of the package that you're running on as well. If you can pin down that that you are in your original package, then you know something about the safety in which you are running. So you can write ad hoc checks. It's certainly possible to write a root check that looks for SU in locations that you expect it to be on a rooted device, but really those are hard to maintain in general. Naive root checks are pretty easily circumvented. There are a lot of tools for doing so. If you've heard of SU hide or Magisk, they're there to essentially let people run banking apps or Pokemon Go, whatever you want on their rooted devices. Also, I'm going to do a quick demo, essentially the same Gradle build, but I've injected a tamper check into the application. And something is happening with my mouse. I think it's stuck to the, I think it's bounded to the emulator window somehow. I'm not sure if I understand why. Oh boy. All right. I'm afraid I can't really, without the use of my mouse, actually get over to the emulator and... actually... I guess it's not the bounds of the... So yeah, now when I try to launch the app, it crashes because we tampered with the app and we re-signed it. Actually, maybe... And... Oh. So yeah, if we look through logcat, it's issuing a class circularity error with no real stack trace. Okay. So, I guess my conclusion would be that protections are better together. So for the sake of simplicity on that last demonstration, really to make it simple to tamper with so that we can see the tamper check in action, I disabled the obfuscation features. But really, if you want optimal protection, you want to use all of the protections available to you together. Obfuscation and string encryption and control flow obfuscation protect your checks. They make them harder to locate in the code and potentially disarm with hooking or debugging. Checks make it easier to protect your obfuscation. They make it harder to step through the code and follow the flow of control through it. They make it harder to undo string encryption on your code. So, the analogy that I put here is peanut butter and jelly. They're both good alone, but they're much better together. All right, so I have a lot of image attributions because I have a lot of images. I don't know if you can read any of them. Oh yeah, you can, yeah, thank you very much. If you want to say hi, or if you find a question, you can stop by our booth before we leave. I'll be happy to talk to you. We don't have it up yet, but we're planning to put up some of the demo that I showed you today on our GitHub repository. And yeah, thank you.